Hi everyone, Mrs. V here, and today we are going to learn about the amines. So let's get our PowerPoint on and learn a whole lot more about these stinky compounds. Amines get a pretty bad rap for their smell, and rightly so. They are responsible for the smell of dead bodies. However, there is a lighter side to amines, because amines are also present in coffee and in chocolate. Let's find out more. Both primary and secondary amines can form hydrogen bonds between the amine molecules. So if we have a look here, the nitrogen is delta minus, and of course that has the non-bonded electron pair as well, and the hydrogen is delta plus. And so in a neighbouring molecule, we can actually get that particularly strong dipole-dipole attraction that we call hydrogen bonding between molecules. There is more hydrogen bonding possible between primary amine molecules because they simply have that extra hydrogen attached to the nitrogen. However, secondary amines can still form hydrogen bonds. We still have the delta minus on the nitrogen and the delta plus on the hydrogen. Tertiary amines don't have a nitrogen to hydrogen bond, so they don't form intermolecular hydrogen bonds. Now, the nitrogen to hydrogen bond is not as polar as the oxygen to hydrogen bond, so this hydrogen bonding between amines is not as strong as the hydrogen bonding between alcohols, and therefore we would expect that to have an influence on their properties. So amines do have higher melting points and boiling points than alkanes because they can hydrogen bond, but because that hydrogen bond is not as strong as for alcohols, their boiling points will be lower than alcohols. So if we compare an alkane, an alcohol, and an amine of similar molecular mass, we see this evident in their boiling points. So here we have ethane, methanol, and methanamine. They are all of similar molecular mass, and that's important because that means the dispersion forces are equal between these molecules, and therefore any differences we see in their boiling point is due to something other than their dispersion forces. So we see here that the alkane has the lowest boiling point, the alcohol has the highest, and we have our amine as an intermediate. Same thing, even if we look at propane, ethanol, and ethanamine, again, similar molecular masses, and we see that same trend where the alcohol has the highest boiling point, the alkane has the lowest, and the amine is in between. If we look here at the graph of boiling points, we can see that the effect is most pronounced for the smaller molecules. And that is because the dispersion forces are so small, there's a much greater influence of the functional group on the physical properties. As we see our molecular mass increase, then we notice that there's less of an effect for the heavier substances because the longer carbon chains of those molecules mean that the dispersion forces are now having much more of a dominant effect on the properties of the molecules. Tertiary amines do not form intermolecular hydrogen bonds because they don't have a nitrogen to hydrogen. However, there is still a non-bonded electron pair on the nitrogen, and that is still delta minus. The carbon are delta plus, and there will be dipole-dipole bonding. All amines are able to form hydrogen bonds with water, which means they all have some degree of water solubility. Even the tertiary ones can still hydrogen bond with water. Even though they don't have a hydrogen, water is able to provide the hydrogen for that bonding. So amines with between 1 and 6 carbon atoms are water soluble, But of course, as with the number of carbon atoms increases and the solubility decreases as the dispersion forces start to dominate the properties of the molecule. We can see here that there is more extensive hydrogen bonding available with water and a primary amine than water and a secondary amine. So we would expect primary amines to be the most water soluble, followed by secondary, and then tertiary has the least hydrogen bonding with water. So they would be the least soluble. The odour of amines, the lower ones that are actually reasonably volatile and therefore have a noticeable odour. The very small ones like methanamine, ethanamine have fishy odours. The larger ones, things like putrescine with its 4 carbon atoms and cadaverine with its 5 carbon atoms, you can just imagine that they are so named because putrescine smells disgusting and cadaverine is the smell of a dead body. So when you drive past a dead kangaroo on the roadside, what you're smelling is those amines. Chemical properties now. Amines are weak bases. So they're just like ammonia is a base. Ammonia has a non-bonded pair of electrons on the nitrogen atom, and that makes it able to accept a hydrogen ion and therefore is a Bronsted-Lowry base. What it forms is the ammonium ion and of course the hydroxide ion because it's a base. When it comes to amines, we still see that non-bonded pair of electrons on the nitrogen, and therefore the amine is able to accept a hydrogen ion. So making that a Bronsted-Lowry base. It is a weak base, therefore we use the equilibrium arrow. And the species formed is similar in its structure to the ammonium ion. This is called the alkyl ammonium ion. It is a coordinate covalent bond between the nitrogen and the hydrogen, or you may know that as a dative bond. And the positive charge is spread across the entire molecule, and therefore we put the molecule in those square brackets and put the charge outside the brackets. Let's have a look at an example. Here we have methanamine. It's going to accept a hydrogen ion, and what we form is called the methyl ammonium ion. This means that the methyl ammonium ion will be produced when an amine reacts with an acid such as hydrochloric acid. If we have ethanamine reacting with hydrochloric acid, then we're going to have the hydrogen from the acid being bonded to the nitrogen of the amine. This will make, I'm just going to draw this the other way around. So this will be NH3 plus, Cl minus. And because that will be the ethyl ammonium ion, this is ethyl ammonium chloride. Pause the video and have a go at butane 1-amine reacting with nitric acid. We'll be back with the answer. Okay, so we have the hydrogen from the acid bonding to the nitrogen of the amine. We'll make NH3 plus, and this time it'll be the nitrate ion. So this will be butyl ammonium nitrate. Amines are also able to undergo condensation reactions, and the condensation reaction between amines and carboxylic acids is very similar to the condensation reaction between alcohols and carboxylic acids, which of course forms esters. So you'll remember from our work on the esters that there is polarity in the carbonyl group on the carboxylic acid. And this means that the non-bonded electron pair on the nitrogen is going to be attracted in to that carbonyl carbon. What will happen then is water will be eliminated. So we will take the hydroxyl group from the carboxylic acid and one of the hydrogens from the amine, and that will go into forming our water. And when water is formed in a reaction, we call it a condensation reaction. The product, the organic product, is called an amide. The technical IUPAC name to say that is it's an alkyl alkanamide. It's named very similarly to the way esters are named, except instead of OH on the end of the carboxylic acid's name, we have amide on the end. Okay, the amide group links two carbon chains together, very much the same as an ester. So we have two separate alkyl groups being joined together. And in biological reactions, we call the amide group a peptide. So this is known as a peptide link if we're looking at biochemistry. Let's try some examples. Methanamine and propanoic acid. Let's draw methanamine out. Going to draw the hydrogens out separately. And propanoic acid, what we're going to have here is this non-bonded electron pair on the nitrogen being attracted in. We're going to eliminate water. So we're going to eliminate a hydrogen in this hydroxyl group and produce our amide. This is an equilibrium reaction, requires a strong acid catalyst. So we will have, generally when we write the amide out, we write the carboxylic acid part first, and of course, water is formed. Now, the naming of the amide, similar to the naming of the ester, we had methanamine and propanoic acid. So the alkyl part comes from the amine, so this will be methyl. And the amide part comes from the carboxylic acid, so this will be propanamide. Pause the video and try butan-1-amine with ethanoic acid. We'll be back with the answer. Okay, butan-1-amine, 2, 3, 4, and our amine. And ethanoic acid. And we are going to form in an equilibrium with a strong acid catalyst. And water. What will this amide be called? Butyl from the butanamine, butyl ethanamide. Now, I've got a challenging example for you. We are going to look at this particular compound, and we're going to see that this is what we call an amino acid because it has an amine group and a carboxylic acid. Because it has an amino group and a carboxylic acid group, it's able to undergo amide formation with another molecule of itself. Let's have a look. I'm going to draw it out so that the hydrogens are a little bit more obvious. So I'm going to draw my amino group on the end. And then I'm going to draw my carboxylic acid. I'm going to color code the next molecule so that we can see which one is which. What will occur is exactly what we've seen happen with normal amide formation. The non-bonded pair on the nitrogen will be attracted to the carbonyl carbon, and we will be eliminating water. And I'm going to work down the page here. We'll need a strong acid catalyst, and let's have a look at what's produced. Now we have our amide link. And we'll have water formed as well. But I want you to notice something. I want you to notice that there is still an amine and still a carboxylic acid in this group. So this can react again. Let's react this with a third monomer. And of course, what will happen is our non-bonded electrons on the nitrogen are going to be attracted into the carbonyl carbon. And with a strong acid catalyst, we're going to eliminate water again. And we will get, it's getting tricky, our original amide link now we've formed another amide link. And of course, we'll also get water. But have a look. We still have an amine and we still have a carboxylic acid. So this can react again. I'm not going to go through, I think you get the idea that this is just going to keep adding yet another monomer and another monomer on. And what we're going to form here is called a polyamide. Many amide links, and the natural polyamides are called proteins. So this is protein synthesis. Let's have a look at where we find amines in our everyday life. Well, close to my heart is caffeine, and even closer is chocolate. Not so much morphine, but I'm sure that if I'm ever in a situation where I have a lot of pain, I may appreciate that as well. So you can see caffeine contains a tertiary amine here, a tertiary amine here, another one there, and another one there. Theobromine, tertiary amine here, secondary amine here, tertiary, tertiary. And morphine contains a tertiary amine here. Amines are present in neurotransmitters. Now, neurotransmitters are substances that relay messages in the brain. And you can see We have chemicals that make you happy. There you go. Amines make you happy. Some of them stink. These ones are too large to actually stink. They wouldn't be very volatile. So we have serotonin, dopamine, oxytocin, and endorphin. These are all chemicals that relay messages in your brain to make you feel happy. The nerve impulse is relayed from one nerve cell to the other through a chemical reaction in which these neurotransmitters are released and they actually diffuse across the gap between nerve cells and they are picked up on receptors in the next nerve cell. So all of these molecules are neurotransmitters. Neurotransmitters are generally small molecules that contain amine groups. So we have adrenaline, dopamine. Dopamine makes you feel extremely happy. It's your reward chemical. We have serotonin. Endorphins are released when you exercise, and they are good pain relief substances. And we have oxytocin. In humans, we have histamine found in nearly all tissues of the body. It's actually stored there and it's released when you are injured or you have an allergy or an infection, and it plays a really important role in your body's immune response. It actually causes your blood vessels to dilate so that your white blood cells can rush to the area and fight infection. A lot of fluid can rush to the area to swell it up so that if there's a substance that's inadvertently got into your body that shouldn't be there, it will be actually immobilized in that area. And histamine also is a neurotransmitter. We have nicotine. Nicotine's found naturally in tobacco leaves, and that is an addictive substance. A lot of the amines are addictive substances. This is found in cigarettes and also in vaping chemicals. Just notice in here with caffeine, theobromine, and theophylline that very small changes to a molecule can actually be very significant. So have a look at the similarities between these three molecules, and you'll notice that they vary only in very small detail. So the difference between caffeine and theobromine, so coffee and chocolate, is simply the presence of a methyl group at that point in the molecule. And the difference between theobromine and theophylline is just whether or not we have a methyl group here. And of course, the methyl group versus the hydrogen. So they're very, very small changes, and yet that can have very significant effects on the properties of the molecule. So caffeine, we find, I like to think of caffeine as pleasantly addictive. It's what draws people to coffee. Chocolate, also pleasantly addictive. The theobromine is what actually draws people to keep eating chocolate. And we come to theophylline, and that's actually a bronchodilator. So this is a prescription drug. And we find that many pharmaceutical products are produced from natural amines. Dopamine is your natural neurotransmitter, and have a look at the similarities between methamphetamine, which is a synthetic amine, and dopamine. We can obviously see that we've lost the hydroxyl groups at these positions here, and we've picked up a couple of methyl groups. Methamphetamine is used to treat attention deficit disorder, or ADHD. It helps to increase your ability to pay attention, to stay focused, and it controls some behaviour problems. It might also help you organise your tasks and improve your listening skills. We see pseudoephedrine is also related to dopamine in structure. We see what's happened here is we have a methyl group on the end and a hydroxyl group having been introduced to the molecule here. And pseudoephedrine, or Sudafed, as it's marketed as Sudafed, it relieves nasal congestion that's caused by colds, allergies, and hay fever. It can relieve sinus congestion and pressure. So these are synthetic amines that are actually based on a natural amine. We see codeine. Codeine is a synthetic amine that is produced from morphine. Codeine is a pain relief medication. It has become a prescription-only medication now because even in low doses, it was found to cause opioid tolerance. You know, morphine, heroin, and codeine are all opioid chemicals. Morphine is naturally occurring in opium poppies and is produced, it's used to produce codeine, and this is now, you know, on the prescription list because it was seriously quite addictive. We have diazepam, is another synthetic amine. It's marketed as Valium, and that's used to treat anxiety, alcohol withdrawal and seizures, sometimes muscle spasms. Sometimes it's used to sedate people before medical procedures. We didn't really talk much about heroin on the previous slide, but I want you to look at the structure of morphine and the structure of heroin. And I want you to identify the differences. Do you see that where morphine has hydroxyl groups, heroin has ester groups? So heroin is just the ethanoate ester of morphine. Now, you know how to produce heroin from morphine because we've studied this reaction. So how do you turn an alcohol into an ester? If you want an ethanoate ester, you'll need to add ethanoic acid. You'll need a strong acid catalyst and you'll need to warm it up. Do not try this one at home. This is seriously illegal to do this. You are not to go home and make yourself illicit drugs. However, you'll find amines in many illicit drugs. So cocaine has an amino group. You can see cocaine here. And we see lysergic acid diethylamide here has an amide group. And this is known as LSD. No Breaking Bad for any of you, sorry. You cannot do this, it's illegal. Right, proteins we mentioned before are polyamides produced from amino acids. So amino acids have both an amine group and a carboxylic acid group. And what's really interesting about this is that means they're able to undergo an acid-base reaction within their own molecule. So this hydrogen can actually be lost to the nitrogen on the amine group, and this forms what's called a zwitterion, as in two ions on the molecule. So we actually end up with an ionized and a non-ionized form. So if we have a look at the amino acid asparagine, we can see here that it's an alpha amino acid, meaning that the carbon here that bears the amino group is right next door to the carboxylic acid group. And being so close, then we can actually have this hydrogen from the acid donated onto the amino group to form the ionized form, which is called a zwitterion. When amino acids undergo amide formation to form a polymer, which is known as a protein, then the structural formula of the polymer is not usually shown, simply because the formulae of the amino acids themselves are reasonably complex, and therefore having a great chain of them all linked together is just going to make a monstrously large chemical formula. Generally, the amino acid sequence is listed using the abbreviations for the amino acids. So each of the little circles here is an amino acid, and in between we would assume that is an amide link. Or as this is a biological molecule, we would call that a peptide. There are synthetic polyamides as well as natural ones. The natural polyamides are the proteins. The synthetic ones are called the nylons, and they're produced from diamines and diacids in an amide formation reaction. And these are part of our everyday lives. Nylon 6,6, very common polymer, makes sleeping bags, ropes, dental floss, hoses, the straps of your seatbelt, used to make tarpaulins. Another common one is Kevlar. It's produced from terephthalic acid and phenylenediamine, and that makes bulletproof vests, diving gloves, walking boots, military helmets, very, very tough polymer. So as you can see, amines and amides are all around you every day. Well, that's all for today. If you enjoyed learning more about the amines, then please consider giving this video a like. And as always, please subscribe to my channel, watch a few more videos, and keep learning more chemistry. I'm going to see you guys in the next video.